The integral test is a pretty nice test to test for convergence. We start by looking at tests of convergence for series with these positive terms. First of all, we have to have positive terms. So if f is positive, this is a function, f of x, is positive and continuous, and an equals f of n, which is decreasing for x greater than or equal to 1, and an equals to f of n, then this infinite series n equals 1 to infinity of an, and the integral from 1 to infinity of f of x dx either both converge or diverge. Whatever they're going to do it together. So what this is saying is, if I'm trying to figure out whether this series converges or not, I can think of it in terms of f of x, and then take the integral, and if the integral converges, then I know that this series will converge. Now, I'm not going to go through a proof on this. I'm just going to do a couple things here to suggest that it might be true. So, let's see, I have 1, 2, 3, 4, 5. That's enough to get us the idea. Let's say this is f of x. F of x starts right here, and it's a continuous function. And obviously, asymptotically, it has to go to 0, or else the integral, if I were to integrate this, I'm not going to end up with a finite number. Now, my series starting at 1, if I think of the area under the curve based on the series, if I think of the distance between 1 and 2 as being 1, then I come up to the curve, I basically have a box. And this box has area equal to A1, because it's 1 times the height, because up here would be A1. And then this box has area that's equal to A2, because it comes up as high as A2 does, and so forth. So I could, if I add up the sequence or the series, if infinite series, I can think of it as an area that could represent in these boxes. Now this is kind of like a left-hand box sort of a thing. Well, I could also think of this as a right-hand box, which my first box would look like this, my second box like this, second like this, second like this. And you remember from Calc 1, the idea was that if we do the right-hand and left-hand boxes, and in the limit, as I take an infinite number of these, as delta x goes to 0, these two converge to each other. And I'm not going to get deep into any type of proof on it now, but I'm just simply going to suggest to you that it seems reasonable that if f of x converges, the area under the curve, when I say f of x converges, I'm talking about this blue area under the curve, that this area represented in either the red boxes or the black boxes should also converge. It just seems like a reasonable sort of thing. Again, I'm not going to get deep into any kind of a proof, and what I did is far from a proof. I'm just trying to suggest that it's a reasonable sort of thing to do. You can actually look in your books. I'm sure your book will actually go through a nice proof for you. So I want to take a look at this first example here. I want to try to figure out whether or not this thing is going to be convergent or not. So what I'm going to do is I'm going to compare this with f of x equals x over e to the x. Now notice f prime of x, if I take the derivative of f prime of x, this is going to be equal to a negative 1 over e to the x, because this negative would come from the e to the x down here, which is decreasing clearly everywhere, at least in our domain here. For x negative, that's another story perhaps, but we don't really care because we're lining up x with our ands, which starts at 1. So this thing's definitely decreasing. Our function's decreasing. I'm in good shape there. What I want to do now is I want to integrate this thing. So I'm going to take a look at the integral from 1 to infinity of x over e to the x. Actually, I'm going to rewrite that. I'm going to write this as x times e to the negative x dx, which is equal to the limit as b goes to infinity of the integral from 1 to b, because this is an improper integral, of x times e to the negative x dx. Now, I need to do this by parts. Straight u substitution won't work. So let's see, how do I want to do this? How about if I let u equal x, then du equals dx. If I let dv equal e to the negative x, then v equals the integral e to the negative x, which is a negative e to the negative x. So what I have is this, the limit of this integral will be equal to uv, which is a negative x e to the negative x, minus the integral of v du. I'm going to have negative e to the x dx, so it could be a positive e to the negative x dx. So this is going to be equal to negative x e to the negative x minus e to the negative x when I take this integral. Now, I kind of skipped it. I probably shouldn't have, but let's not lose sight of the fact that we've got a limit to deal with here. So what we need is the limit as b goes to infinity of negative x. I'm going to rewrite this only so that when I start evaluating it, you might be able to see what's going on a little bit better. Negative x over e to the x minus 1 over e to the x evaluated from 1 to b, and b is going to infinity. So this equals the limit as b goes to infinity of, what do I have here? I have a negative b over e to the b, e to the b, there we go, minus 1 over e to the b. That's the first part. Minus, I need this whole thing evaluated at 1, which would be a negative 1 over e to the first minus 1 over e to the first. Now, in the limit, this clearly goes to 0. So what happens to this? Well, I get infinity over infinity. If I apply L'Hopital, this would be negative 1 over e to the b, because remember, it's now a function of b. So I'll take the derivatives with respect to b. And then in the limit, that also goes to 0. So what I end up with here is a double negative. So this is 2 over e. Now, what's important here is the fact that 2 over e is a number. Okay? So it didn't blow up as it. And when I say it's a number, it's not infinity. So the area under the curve for this particular curve is finite. Hence, I can say, therefore, this sum, n equals 1 to infinity of n e to the negative n, is convergent by the integral test. See, I don't know what it converges to. I'm just quite certain that it does, in fact, converge. Now, if this turned out to be infinite, then I'd come back and say it's divergent by the integral test, because they both either converge or diverge together. Let's do another quick example here. I need to know if the sum n equals 1 to infinity of 1 over 4n plus 7 is convergent or not. So I'm going to take a look at the limit as b goes to infinity, the integral from 1 to b of 1 over 4n plus 7, 4x plus 7 dx. Now, obviously, I'm thinking of f of x as 1 over 4x plus 7, which clearly this is decreasing. You don't believe me? Take the derivative real quick, and you see it's negative everywhere in our domain. So now I just need to integrate this. Quick u substitution, in case you don't see it right away. I'm going to let u equal 4x plus 7. Then du equals 4dx. So then what I end up with is du over 4 equals dx. And I now have the integral 1/4 the integral of 1 over u du, which is 1/4 ln u. But u was 4x plus 7. So this is 1/4 ln of 4x plus 7. And actually, I should do an absolute value here. Let's not lose track of this limit. So what I need is the limit as b goes to infinity of, I'm going to pull this constant out because there's no reason to leave it there, of ln of 4x plus 7 evaluated from 1 to b. Well, clearly this is going to blow up. This is going to be 1/4 times the limit as b goes to infinity of ln absolute value of 4b plus 7. Clearly that goes to infinity, minus ln of at 1, this is 4 plus 7, so this is ln 11, who cares what ln 11 is? It's infinite, which equals infinity. Therefore, it does not exist. Therefore, the sum n equals 1 to infinity of 1 over 4n plus 7 is divergent by the integral test.